Periodic properties. In this we will be mainly dealing with the periodicity in the properties of the elements. See, we have been knowing, and that's the basic of our classification of the elements in the periodic table, that the elements, when classified on the basis of increasing atomic number, they show periodicity in their properties. The properties, they repeat after certain intervals, and that is why the elements with these similar properties are placed one below the other in the groups. So we have to study these periodicities in the properties of the elements. What is the basis and what are the reasons for those priorities, and due to this, what all trends we find which actually are there in the periodic table. Now, the first property which is to be studied in detail is the atomic size. See, the most fundamental property, the periodic property, is the atomic size. Now, it is the basis that differentiates atoms of the one element from the other, because definitely as the number of electrons keeps on increasing, the size will keep on increasing. But the most important thing to notice what exactly this atomic size is. Atomic size means the size of the atom. It is usually expressed in terms of the atomic radius. So it is usually expressed in terms of the atomic radius or the radius of the atom, and it is the distance of from the outside the nucleus to the outermost electron. So distance between the outermost electrons from the nucleus is called the atomic radius, and this is the basic property which is actually being used to study the trends in the atomic size. Now, when we say the atomic radius, we must know that how we find out the atomic sizes or atomic radius. There are many techniques by which we find out the atomic radius or atomic size, like some of them are the X-ray crystallographies, in which we mainly find out the atomic sizes of the crystalline solids or crystalline substances. So, whatever the technique we are using, we find out the radius of the atom, and this is how, on the basis of the radius, we define or we study the atomic size. Now, before moving ahead, we must realize that what exactly we do whenever we find out the atomic radius, because it's not possible to have isolated atoms, but the atomic radius is always just calculated for an isolated atom. But practically we know that it's not possible to get the isolated atoms of all the elements. It is only the noble gases which can be isolated, or whose atoms exist in complete isolation. They doesn't combine with the atoms of the other elements or with the atoms of the same type, so that they doesn't form molecules. So their atoms can be taken in isolation very easily, but we cannot have the atoms of all the other elements in the isolation. So what we find is we always try to change them into the solid state, the molecules of the different compounds or the elements, and then through the X-ray crystallography you find out the distance between the nuclei of the two atoms. So if suppose there are two atoms which are just in contact with each other, what we can do is we can find out the distance between the nuclei of these two atoms, and we can just half it. That is going to give us the radius of the atom. The most important thing is that in which form we are taking these atoms, and that becomes the basis of studying the different types of atomic radius. Now, the atomic radius are of mainly three types. The three types are covalent radius, metallic radius, and van der Waals radius. See, these three types, the basis of classifying the radius into these three types is this, that in what form the atoms are bonded with each other. If they are having a covalent bond, then the radius determined for those atoms are called the covalent radius. If they are existing in the metallic form, then the radius determined for those atoms are called metallic radius. And if they are having no sort of bonding between them, only the dispersion forces or van der Waals forces, then we call the radius determined for those atoms as their van der Waals radius. Let us take these atomic radius one by one. When we say covalent radius, it is mainly done for those homonuclear diatomic species which actually forms molecule, like we have a chlorine atom, or we have hydrogen atoms existing as Cl2 or H2 respectively. Now if let's take an example of chlorine. In the chlorine molecule, what is happening is two chlorine atoms are actually overlapping each other, their atomic orbitals are overlapping, and what we find is that their nuclei are like this. We can find out the distance between the two nuclei, and if we half the distance of between the two nuclei, what we get is the radius. Now we will call this radius covalent radius because these two chlorine atoms are covalently bonded. So their atomic orbitals are overlapping. So the radius which we will get out of this will be very small, will be smaller than the usual value or the actually absolute value. The reason is because the atomic orbitals are overlapping, we cannot find out the exact radius in this case. So this covalent radius therefore is the smallest out of the three. It is the smallest out of the three, and it is always determined, it is actually used for those atoms which are actually forming a covalent bond. Similarly, like we have, suppose, like we can take example of aluminium. Now aluminium, in case of metallic form, will have what? The second type of radius, which is called metallic radius. Now in metallic radius, what we find out that the atoms are, of course, are very closely packed. Their atomic orbitals to little extent are also overlapping, and that's why what we find is that the distance obtained, the radius obtained in these cases is not the absolute one or actual one. It is actually little bit smaller than the actual value, because the atoms in the metallic state are packed very close to each other, so their few atomic orbitals or their atomic orbitals to little extent are overlapping each other. So what we find is that yes, again the metallic radius is little bit smaller than the actual value, but yes, of course, this is bigger than the covalent radius, because in covalent radius there is more extent of overlapping is much larger in comparison to the metallic radius. The third type of radius is van der Waals radius. In van der Waals radius, what we find is it is mainly used, or it is actually determined for those species which doesn't form what molecules. Like we have noble gases. Now since they doesn't combine with each other, like we have neon, argon, of course helium, neon, argon, krypton, xenon, radon, etc. What we can do is we can pressurize them and we can bring their atoms as close as possible under the extreme high temperature, high pressure and low temperature. Now they can come very close to each other. That's called their nearest distance, or near the closest distance they can come to each other. That's called their the minimum distance they can have between the two atoms. And then what we can do is we can find out through the X-ray crystallography technique or by any other spectroscopy method the distance between the nuclei of the two adjacent or very close atoms, and then we can half of this. We can do the half of this so to find out the radius. Now the radius thus obtained, of course, is the largest. The reason is because the atomic orbitals of these atoms are not overlapping. They are not actually in touching each other, or they are in contact with each other. They have a large distance between them. In fact, because they can't come beyond a certain limit, they get what interelectronic repulsions. The electrons of this and the electrons of this, the nucleus of this and the nucleus of this shows more repulsions. So they maintain a certain minimum distance, and what we are doing the half of this. So this is what we have, is that only for noble gases we have no other options because it doesn't combine with any other elements. We can't have there any covalent molecules. So we can't have their covalent radius. It doesn't exist in the metallic form. They are not metals. So we can only have van der Waals radius for these gases. So what we find is, most important thing is, like if suppose we have any atom like A, whose radius by all the three methods is determined, like its radius called covalent radius is also determined, its metallic radius is also determined, and its van der Waals radius is also determined. For the same atom, what we find is that the largest radius will be the van der Waals radius, then it will be its metallic radius, and then at the end the smallest will be the covalent radius. So this is what is the trend, is decreasing order of the atomic radius of the same species when determined in three different ways. Because we can have this atom in the complete isolation, from where we can find out its van der Waals radius. We can have this atom in the solid state, in the more metallic form. So from there we can find out its metallic radius, and we can find out the covalent radius of the same species. So this is what we can have, the different types of radius. The same example we can take is like for sodium. Like for sodium, from its metallic form, we can have R sodium, radius of sodium, which will be what? Metallic, and from NaCl we can have its, or from the sodium, like we can take an example where it is mainly forming a covalent or a bond which is actually is more of a covalent. So like in this case of NaCl, we can have the radius of sodium from the sodium chloride, which will be mainly actually will be its sodium ions radius. So in this case, this will be called ionic radius. My purpose of giving you this example is that you must know this, that we cannot find out the covalent radius of the sodium from here in this case, because NaCl is an ionic compound, and in NaCl, the sodium is not present in the atomic form, it is present in the form of an ion. So the radius, which will be determined by what, doing the half of the distance of sodium and chloride, will only give you what, the radius of sodium ion, not the covalent radius. So these are the certain things which one must know about the radius, that which type of radius we are using in order to find out or do the comparative study, or in order to actually come out with the trends in the periodic table.